All right, so we're gonna kind of begin today by closing out an idea that we were looking at the end of our last lecture. So going back to Friday, we were talking about significant figures, and we had to stop because we ran out of time before we could look at some other factors to consider when we're looking at sig figs. And so one of those things that we want to look at is the idea of an exact number. Now, exact numbers come about for a couple of reasons. For one, sometimes we have exact kinds of conversion statements. So, by definition, for example, there are 2.54 centimeters in every inch. By definition, there are 12 inches in a foot. By definition, there are 5,280 feet in a mile. Those are defined values. And defined values we don't consider in terms of significant figures because those values have been defined and are not measured actually. Same thing is true when we talk about things that we count. So if I want to count the number of steps between here and my office, I'm not going to estimate that value. I'm going to literally walk it out and count as I go. If I want to count the number of people in this room, there's no such thing as a fractional person. I'm going to come up with a whole number that's going to be an exact number. There's no measurement error associated with that. The only error is whether or not I miscount, which hopefully I don't. So those quantities are exact numbers. And when we talk about exact numbers and we use exact numbers in conversions, we have to understand that the rules that we set up for significant figures, those rules that you looked at over the weekend in that assignment, they don't apply to these kinds of conversions. So if I'm using this conversion between centimeters and inches, it doesn't apply towards, oh, well, this has three significant figures in it. I need to round to three significant figures. That doesn't work. That doesn't work that way. This is an exact conversion. It's a defined value. We say that these defined values have infinite precision, meaning they have an infinite number of significant figures. We're just choosing to only show those first three so that we don't have to write down all of the zeros that follow. Now, when it comes to measurements and using mathematical functions, this is a place where in that post-lecture last night, this is where I got some of the questions. This is an easy thing to get messed up and mistaken in your head, especially for addition and subtraction, because we don't use addition and subtraction nearly as often. And when we do, we're usually using values that are measured on the same instrument, so they're going to have the same precision. But let's say that, for example, we are looking at things that are measured on different instruments, and we have to add or subtract or whatever. Well, in addition and subtraction, the thing that we want to be aware of is we know that in each measurement, there is going to be one estimated digit. And that estimated digit is always the last digit that is recorded. So if I look at this example, I know that for this first measured value, the estimated digit is this 1. It's the 5th decimal place. And so when I do the number calculation here in my calculator, I know that that 5th decimal place is an estimated digit because the 5th decimal place was an estimated digit in the numbers I'm subtracting. The problem is there are more than one number that we have to consider. And so when I look at the second measured value, the second measured value has an estimated digit in the 3rd decimal place, the 3rd decimal position, which means that this digit now is also an estimated digit because it is based off of an estimated digit that is linked into the subtraction. So now I have an answer from my calculator that has 2 estimated digits. And I know by rule that I cannot have more than one estimated digit. So where do I go? What do I do to get rid of that estimated digit? Well, this is where I have to use my rules. And so with adding and subtracting, it's all about, if I have multiple estimated digits, I need to round to the value that is the most estimated, the one that is the least precisely known. And the least precisely known one is always going to be that leftmost digit. And so I need to round to this third decimal place. So my final answer is going to have 3 decimal places. Now, how do I know to round that up to 5 instead of down to 4? Well, that's where I have to look at that next door neighbor. That 4th decimal place, that second now estimated digit, is 5 and above. So the rule that we use is simple. If that next door neighbor is 5 or above, we round up. If it's 4 or below, we round down. So since that digit here is a 6, that is higher than 5, I'm going to round this up. And 1.005 is going to be the reported value of my answer. So that's the rule for addition and subtraction. Now, what if I don't have numbers that have decimal places? Well, I do the same thing. If I do this calculation, 10,001 minus 783, my calculator gives me 9218. Question is that the number I need to record? Well, I do the same thing. Where is my last measured digit? Where's my estimated digit? Well, estimated digit here is in the ones place, so that means the ones place is estimated. Estimated digit here in the second one is also the ones place. In this case, both of the values are the same, so I know that I need to round to that decimal place, which means I can leave this one alone. But if I have this scenario, 390 plus 75, well, if I add them together in my calculator says it's 465. But I have to go to my understanding of decimal places. 390, that 0 is not a significant 0. There's no decimal point. So that means that the last digit, the last estimated digit, is this 9, which means that this 6 is now also estimated. And if I compare that to the 5, I have the same kind of scenario I had in the first problem. I've got multiple estimated digits. I need to round to get rid of the extra estimated digits, which means I need to round to the leftmost digit. So I'm going to turn that 6 into a 7 because the 5 is going to round it up. So 470 is the correct answer if we're using our 6-digit rules properly. So with addition and subtraction, we can run into some of these kind of funny gray areas, especially when we get to really large numbers or even really small numbers where we have to figure out where are those good sig figs and where do they end. Multiplying and dividing is a little bit easier. Multiplying and dividing, we're not concerned with where the digits are, we're concerned with how many digits there are. And so all we need to do is we need just to evaluate how many digits are in each recorded number and round to the one that has fewer digits. So in this example, I take these two numbers and I'm multiplying them together. This first number has 4 digits. The second number here has just 3. And so even though my calculator gives me all of this nonsense here, the measurements themselves are going to limit how many of those digits I can record. And so I can only record as many digits as my least precise measurement. My least precise measurement has 3 digits, so my answer can only have 3 digits as well. Now, this one we'll get a lot more practice with, because a lot of the things that we do involve multiplication and division, and not as many involve adding and subtracting. Another question that I got a lot of over the weekend was, what do I do if I have multiple functions in the same kind of problem? So question number 4 in that activity that was due last night, you had to do the subtraction, then the division. The way that you handle those is basically you do all of the functions of one kind. So, usually there's parentheses involved. So we do all the addition and subtraction first, if there are parentheses. And after we do all of those functions of the same kind, we round. Then we do all the other functions, and we round again. So in this particular case, I have 5 digits and 3 digits, 3 decimal places. So I would round my answer here to the 3rd decimal place, to 0.984. I would then take that number and multiply it by the 1.0054. Now I apply my multiplication division rules. There are 3 sig figs here. There are 5 sig figs here. So I'm going to need to round my answer to 3 significant figures. And so 0.988 with 8 as the next door neighbor, we round up to 0.989. And so that's how you would approach that problem number 4 as well. You do subtraction, you round the subtracted portion to the correct number of decimal places. Then you take that subtracted value and you divide it, and you round the final answer based upon the numbers of digits. Where you see that kind of operation most often in the laboratory, when you're calculating percent error, percent difference, those are 2 places where we usually see that, because to calculate a percent difference, you have to first subtract your value from the theoretical value. So you do that calculation, you round it, then you do the division part, and you round it again. So treat each function separately, like it's its own thing, and then combine it. Right. Any questions with these kinds of things related to significant figures? All right, let's do some review questions then. I have 3 statements here, 3 measurements. I want you to pick any or all of the measurements that you know to be exact measurements and not measured quantities like what we would use an instrument for. Chance to get something in? All right, let's see how we do. Okay, most of us are correct. The only exact measurement on this screen is the first one. The only way that we can know the number of steps to get to the top of the Washington Monument is to count them. Now, don't envy the person whose job that was to do it, but that is the only way that you could do it. Because you'd have to literally start at the bottom and count your way all the way up to the top. For these others, we would use some kind of instrument to do this. If I was going to measure the width of the Golden Gate Bridge, I'm going to need some kind of a ruler, tape measure, something to do that. And in using that instrumentation, there's going to be estimation involved. That estimation is the 0.4 part of the measure. For the mass of that golden nugget, same thing. I'm going to use a balance to do that. And even though that balance reads the 4 decimal places, that 4th decimal place is still an estimate. It's not an exact number. Having more decimal places, having more significant figures, doesn't mean that the number turns from being measured to exact. It's still an estimated digit there at the end. All right, I want you to try this one. Now, keep in mind what we just talked about. I've got a multiplication and a subtraction. So at the end of the multiplication, I need to round, and then I need to do the subtraction, and I need to round again. Right, if you're still working it out, go ahead and keep going. Go ahead and get your answer when you get there. For those of us that are finished or nearing finishing, let's just see how we did. So the first part here, so this is a reverse of what you were asked to do in the practice set. Practice set, you had to do subtraction, then division. Here you're being asked to do multiplication, then subtraction. So since the multiplication is going to come first in the order of operations, I need to do the calculation and then round to the proper number of digits. So in this case, it's actually pretty easy. Each of the 2 values that we are given have 5 significant digits. So I'm going to need to round the answer to 5 significant digits as well. So my calculator says that is the product of the 2. If I'm rounding to 5 significant digits, this 5th digit is the one I need to round to, which means that this 5 is going to round it up. I have 78.134. Now I do the subtraction. 78.93 or 78.134 minus 9.3210. My calculator gives me 68.8130. Since I'm subtracting, I need to keep track of where the decimal places are. So I've got 3 decimal places here, but I've got 4 decimal places here. I need to round to the leftmost of those digits, so I need to round that 3. And since the next digit is a 0, I'm going to keep the 3 as it is. I don't need to round up. So 68.813 would be my correctly rounding answer for this problem. Questions with this example? Okay, so we're moving on then. Talk about dimensional analysis. So the overarching technique here is that if I want to convert units, if I want to go from one unit to another, the way that I'm going to do it is I need to go in such a way that I am going to end up canceling units along the way. So that's the scheme in place here. If I want to go from one unit to another, I need to be able to cancel out units along the way. So if I'm starting with unit A in the numerator, I need to have unit A in the denominator of whatever conversion I use so that it cancels out. If I want to cancel out unit B, I need to make sure that I've got one version of that unit in the numerator, one in the denominator, so they cancel out. And all I'm left with is unit C, which is what I'm trying to find in the first place. Now, that's the overall technique. What goes in those little fractions? Well, the whole idea of dimensional analysis is based on the idea that if I multiply an object by something that is equivalent, it's basically the same thing as multiplying by 1. Now, what happens when I multiply something by 1? It's the same. If I have 9 times 1, it's still 9. If I have 35 times 1, it's still 35. So even though from a unitary standpoint, the thing on the top of the fraction and the thing at the bottom of the fraction are not going to be the same number necessarily, if they are equivalent to each other, two equivalent values over each other is like multiplying by 1 over 1, or 8 over 8, or 35 over 35. And so that's what the whole idea here is. If I have a unit that I can convert, a unit that I can tie together with another unit that I know the equivalent nature of, I can use that equivalent statement to convert one to the other. So take this particular example. 8.91 inches, we're converting it into centimeters. So if I start with my 8.91 inches, the conversion factor that I'm going to use is the idea that I know that 1 inch is the same as 2.54 centimeters. So if I set up my fraction, I need to put inches in the denominator so that it cancels out the inches here in the numerator, and centimeters in the numerator so that it's left over by the time we get to the end of this. What is the equivalency? Well, that's what the values here are for. 2.54 centimeters in 1 inch. My inches cancel out. I'm left with just centimeters. Now I can go about the work of just doing the calculation. 8.91 multiplied by 2.54. My calculator says this, 22.6314. Now here's where my rules for sig figs come in. This is a multiplication. I need to use the correct values. How many digits did I start with? I started with 3. This is an exact conversion, so it doesn't play into the roll. I need to round this to 3 digits as well. So the third digit is the 6. And the 3 is going to cause that 6 to stay where it is. 22.6 unit is centimeters. That is my complete answer. So 22.6 centimeters is the correct value for 8.91 inches when we convert. General rule of thumb. I use the word general here because you should always do the sig fig application when you can. But generally speaking, the number of significant figures that you start with as far as a measurement are concerned are usually the number that are going to be spit out at the end. Usually with conversion factors, even for the ones that are not exact, we usually can know the conversion to enough significant figures that it doesn't limit our original measurement. And that's usually what we aim. We don't want to limit our original measurement in any kind of way. The only times where that comes into play is when we have things that are out of our control. Let's take a look at a couple of other examples. So here's a metric conversion. Now, the metric table that we talked about, remember, you are responsible for knowing the multipliers and how to work within the metric system. Most of the conversion factors outside of the metric system will give you in some kind of way. But you need to know what the prefixes mean and how to apply them. So if I take 321 nanometers and convert it into meters, I have to understand, okay, 321 nanometers, what is the relationship between the nanometer and the meter? Now, to answer that question, we would be easily able to go to our prefix table and say, okay, the multiplier there is 10 to the negative 9. What does that mean? Well, that's where this note that I put in here helps. If I'm using the conversion factor table, that prefix multiplier goes to the base unit. That 10 to the negative 9th goes on the meter, like so. So there are 10 to the negative 9th meters in every nanometer. Now, there are other ways you can do that conversion factor. If you know that nano means billionth and you want to write it the other way, 1 meter is 1 billion nanometers, you can do that. You're going to get the same result. But if you're using that table as kind of your guiding star here as you're starting to learn what the prefixes mean, just make sure that you apply it properly. That multiplier, whatever it is in scientific notation, that goes on the base unit. So if the base unit is seconds, it goes on the seconds. If it's meters, it goes on the meters. If it's liters, it goes on the liters, so on, so on, so on. 321 times 10 to the 9th, negative 9th, will give me, in scientific notation, 3.21 times 10 to the negative 7 meters. All right, let's take a look at another example. 341 deciliters to milliliters. Now, I made mention on Friday, deci is not going to be a prefix we encounter often. But what do you do if you do have some kind of conversion like this where there is not a direct link? So if I go to my conversion table again, I'm going to see deci and milli, but I'm not going to see anything here that tells me the difference between the two. So how do I handle that? Well, there's a couple ways you can go it. The way I would do it is I would convert to the base and use the base as my conversion. So this would actually take 2 steps. 341 deciliters. First step would be to turn deciliters into liters. And then the second step would be to take liters and turn it into milliliters. Do my unit cancellation, just make sure everything comes out, and it does. So I'm going to end up with milliliters, which is what I wanted. Now I just have to remember what the prefixes do. Deci is 10 to the negative first. So 1 deciliter is 10 to the negative first liters. And there are 10 to the negative third liters in 1 milliliter. So putting this together, 341 multiplied by 10 to the negative first, divided by 10 to the negative third. I get 34,100 milliliters. Since all of our metric conversions are exact, metric conversions never have to worry about messing around with sig figs. Whatever number of sig figs we start with, that's what gets spit out at the end. One other thing with metric conversions is, since everything's based on powers of 10, you can slide your decimal around if you don't want to deal with the dimensional analysis aspect. So in the case of the first one, that might be a little bit difficult to do. You got to slide that decimal 9 places to the left, but you can do it. For this one, you have to slide it one to the left and then 3 to the right. But you could do that as well. The reason I would do the dimensional analysis is just because it's organized. We keep track of our units pretty easily. So that lessens our chances of making a mistake. All right, go ahead and try this one. Convert 300 milliliters into microliters. For this particular one, do not use scientific notation. Do not include units, because Top Hat will mess up the interpretation of your answer if you put in units. Micro. This is micro. So just to save you a little bit of time, one liter is equal to 1,000 milliliters. It's also equal to 1 million microliters. All right, if you're still working out your answer, go ahead and keep going. For the benefit of our time, though, we'll get this started. So 300 milliliters is our starting value. And so we want to turn this into microliters. So a couple ways to do it. you really use either of these directions, you'll get the same thing. So if I use the ones on the left, there are 1,000 milliliters in a liter. My milliliters cancel. I now have liters. I can then look at it and say every liter has 10 to the 6th, 1 million microliters. Liters cancel. I'm left with microliters. And so 300 times a million divided by 1,000. You get 300,000 microliters. How many significant figures are in this particular answer? Just one. Our initial measurement doesn't have a decimal place. So we have no way of knowing how many significant figures there are unless we have either that or scientific notation. So our best guess there is that we have just the 1 sig fig. If we only have the 1 sig fig, that means that we're only going to carry 1 sig fig in our final answer as well. So 300,000, or if I did put it into scientific notation, which I know it says not to, it'd be 3 times 10 to the 5th. All right, questions here? Okay, so we're going to talk about some special cases now. So doing dimensional analysis inside of kind of the framework of easy metric conversions or easy English system conversions, we can kind of follow that up. What if I have conversions that have exponents? So what if I have to deal with square inches or cubic inches, cubic centimeters? Well, the trick there is that basically the conversion is the same. The exponent just tells us how many times we have to do that conversion. So in your book, it talks about, if I want to convert 32 cubic inches into cubic centimeters, I can cube each side of the conversion and come up with a new conversion factor. So if I cube 2.54, I get 16.4. If I cube 1, I get 1. I have a new conversion factor to look at. That's one approach you can take. The other approach you can take is simply just to do the conversion however many times the exponent tells you to. So if I have 32 cubic inches, I know that the conversion between inches and centimeters, every inch is 2.54 centimeters. I can do that conversion 3 times over. And I'll end up at the same result. Inches times inches times inches is inches cubed. So they cancel out in turn there. Centimeters times centimeters times centimeters is centimeters cubed. And so if I take 32 times 2.54 times 2.54 times 2.54, I'm going to get the same answer roughly that they do. My calculator says 524.386 because I didn't round the conversion off here. But by the time I get to the 2 significant figures, I get the same 520 cubic centimeters. Again, 2 sig figs there because we only started with 2 in our initial measurement of that area or of that volume. So On Friday, we got a little bit of cleanup here, talking about density and just using density as a conversion factor of its own. We have some combo units that we can talk about, which coincide with what we see in recitation on Friday as well. And we'll also start chapter 2 and module 2 and get that going. So this assignment, I want you to do it anyway for tomorrow. I think you probably can kind of figure it out, but if you do have questions, take advantage of that feedback, send me some questions in your mind or email, and I'll start Friday after the elements proficiency talking about those. Have a great day.